Hey guys, my name is Matt LaVoy. I am a compositing supervisor over at Scholar. This is a walkthrough of a particle-based paint stroke effect that we recently developed for an Xbox trailer for a game called Aura, where we have this continuous fly-through revealing all these different imagined game environments that have been treated with this stylized look. This is scaled up here so you can see the brushstrokes in more detail. This effect was applied as a post-process to our lighting comps. That way we could better control the look of the painterly style in parallel to the CG comps underneath it during production. Here you can see the strokes isolated. These are being generated through a series of custom BlinkScripts that I'll share that are driven by the render camera and world position from our CG renders and then putting that back on top of our comps by iterating an array of customizable brushstroke textures. Typically, one of the challenges with doing any kind of paint effect like this is getting consistent results between frames without a lot of flicker. But because this is all based on the position of the CG, it's very stable. And you can see that even the rotation of the strokes matches really well to the contours of the underlying image. The density, the size, the color, and the orientation are all easily adjustable with this setup that I'll demonstrate. Now to jump into the actual Nuke scripts for these effects, I wanted to start from scratch and then build up all these connections so that I can better demonstrate how everything is working together. So to start out, we have our final art-directed, color-graded CG comp here. And then we also have our original CG renders out of Redshift here. And this is just raw lighting without any comp applied. And this has all of our standard lighting and utility AOVs included. And then we have our render camera here, which has been generated from the metadata from this EXR sequence. And lastly, we have a series of brushstrokes here. I can supply these along with these BlinkScripts. One is for converting the position AOVs into the formatted particles, and the other is for scattering these brushstroke instances onto those particles along with some additional info. Before we connect these together, we want to look at the world position AOV to make sure that it's coming in correctly from our renderer. In this case, we're working with Redshift, and we currently have two different world position AOVs. One of them is being anti-aliased, which is when the samples are being filtered together, and you'll notice that the edge values fall off into the background values, and this is probably the default setting in most renderers. So then alternatively, we have this other confusingly named P-filter AOV, which is the unfiltered version where the position values are not being averaged together. And this is the correct one for this effect because it's unfiltered. It's going to give you a much more consistent result when you're trying to project this out into particles. Another quick deal to point out is because we're working with Redshift, we need to actually flip the Z around because for some reason with Redshift, it comes in backwards. So we're just going to use a grade to negate the Z channel while making sure we're not clamping our negative values while we're doing that. And then we can verify this by looking at the position to points and setting this to P-filter. Now we can see that our world position is lining up with our render camera frustum. So with our world position ready to go, we can start to set up our first BlinkScript labeled position to particles. So first I'm going to change this here so I'm shuffling the result of this flipped Z channel for Redshift. Now I can delete this and I can connect this BlinkScript to our world position shuffle. And then we need to make sure our camera is connected as well. So to connect the camera, we just expose the world matrix. And then we can expression link this here as well as our focal length here and our horizontal aperture here. Also making sure that we have a full alpha channel. And so right now, this doesn't really give you any different result from the original position output, but that's because we still need to affect our world position so that we can start to control the density of the particles that we want for our brushstrokes. So before we actually do that, I want to point out that the current position values are problematic because you can see that we have all these decimal values. And while it's necessary for most cases, we actually want to limit these values so that we can get consistent positions between frames. Because right now we pretty much never see the same position value twice over multiple frames of animation. And we're also going to be creating particle IDs from these positions. So it's even more important that we limit these position values. So to do that, we can actually just round these decimal numbers down into integers using a very simple expression through the expression node.
By rounding the values, we were basically just forcing all the neighboring pixel values to all share the same value, which reduces the density of the particles while also removing any inconsistencies between multiple frames and gives you a much more stable result. So now when we sample these values, you can see that the positions are limited to just integers, and we can now start to control the density by multiplying the values before the expression node and then inverting that same value after the expression node with two grade nodes that are expression linked together. When I start to multiply the values before the expression, you can see we can increase or decrease the density by manipulating how these values are being rounded. This way we can control the right amount of space we want between these points so that our brushstrokes can be applied without getting completely muddy on top of each other if the particles are too dense. The next thing I wanted to highlight won't be part of this setup, but I quickly wanted to demonstrate that we can actually use a separate camera from our render camera, or in this case, we can offset our current camera, and this allows us to view these positions from other angles. This could allow you to come up with a lot of other uses for this effect. I've been able to use this for time-lapse motion effects, or even exporting position data out of Houdini as EXRs using VexCops for visualizing position values from other particle sims or even dense particle environments by scattering points on environments in Houdini and then visualizing them within Nuke. So right now we have these evenly distributed voxel grid looking particles, but we actually want to randomize them quite a bit so that the brushstrokes feel more naturally placed. So to do that, we can just apply a 3D noise to our integer position values, which would look like this, where you can see how the rounded values makes the noise look more blocky. If you don't already have a 3D position noise tool, I can quickly show you how I made this one. Here inside this group, I have these 3 expression nodes for each axis, where I'm using an FBM noise expression that Nuke provides documentation for. Here in this page, you can actually see the expression and then the different inputs that it's expecting. So then this returns positive and negative values that you can use to add against your world position values. So with our 3D position values set up, we can plus this over our world position values to start to offset the points away from the graded particle look. Depending on your scene scale, you'll probably need to add an additional grade to multiply the values without clamping the negative values. And because this noise is also being driven by the integer values, it will also be very consistent between frames of animation. I didn't set it up this way on this project, but if you wanted your particles to stick with your character animation, you would simply use your PREF AOV instead of your world position. That way the points could always move along with the rest position of your animated objects. So with the scaling and noise control setup, we now have a result that starts to give you a nice scatter effect of the particles that stays consistent over animation. And because this is running through a BlinkScript on our GPU, it's extremely fast to work with, even though we were iterating over millions of particles. I also wanted to point out that the output of this result is the new adjusted position values in the RGB channels, as well as the distance from camera in the alpha channel, which is used to figure out the size of the 2D brush textures and the next BlinkScript. Now that we have our particles created as a template to place our 2D textures, we can load all of our individual brush strokes. I've supplied these as an image sequence that I'm going to load in individually to make the connections more simple, but you can obviously set this up using your own textures or even figure out how to create these procedurally. So if we take the second BlinkScript here, we connect our particle position to our particle output, and then we can take our final comp or whatever reference image you were using and connect this to our particle color input. And then we also have a third particle info input, which I'll explain in a second. But for now, I'm just going to put a constant as a placeholder so we don't get any BlinkScript errors while we're testing out the result. And then for these 12 brush input textures, I'll have to connect all these to our inputs, but I'll quickly pause while I do that. With everything connected, we view the result and we see the colorized individual brushstrokes coming through, but they need to be scaled up quite a bit. And after we do that, we'll notice that right now they're all look like they're using the same texture and they're all rotated the same direction. And this is because we still need to set up our particle info input
to adjust the rotation, the particle texture ID for assigning which texture to use, as well as an optional per point scale attribute. So first we'll start with the particle texture ID, and we'll do this by first assigning a unique value to all these particles. To start with, we'll create an expression that gives us a random number based on each of the X, Y, Z position values. That'll create some random numbers with lots of decimal values that will be unique to each world position value, and it will stay consistent between frames since we are sampling our static environment. So now we have all these random numbers showing in our alpha channel, but we actually want to set this value so that it's only outputting random integer values between 1 and 12 to correspond with our 12 brush textures. So to do that, we can use a second expression node where we first move our decimal value by multiplying by some large number like 10,000. And then we can round this into integers to remove the decimal values. And then we can get the modulus value from this, which basically returns the remainder value after dividing by 12. And now this cycles between 0 to 11. So then we add 1 and we have a random number that cycles between 1 and 12. Next, we'll take this brush ID value and shuffle this into the alpha channel of our particle info input. So with that, we can see our brush strokes are coming in correctly with lots of variation within the different brush strokes, but it still looks a little disconnected from our reference image without any rotation being affected. Next, we'll look at creating a 2D screen space direction vector from our reference image so that we can match our brushstroke rotations to the contours of our image. For this next part, I wanted to sidebar the demonstration a bit because I think this was one of the aspects of this effect that I was the most excited about figuring out, and I think it should be explained a bit more in depth. Also, I think this concept could be expanded further for a lot of other effects if someone were to take the BlinkScripts that I'm providing and start trying to write their own effects different from what I've presented. To start out, we're trying to take our reference image or this final comp output, and we want to figure out how to get these brushstrokes to flow along the same direction as the obvious horizontal and vertical contours within our image. So to do that, we can create some custom direction vectors using the matrix node. Now, if you look up the convolution matrix or kernels online, you can find a lot of examples of how this is used for tons of low-level image processing. You can find this Wikipedia page here, for example. This is used for common filtering methods, but in our case, we'll be using two separate matrix kernels, one for finding changes in horizontal values and one for finding changes in vertical values. And here, if you plus these together while isolating just the red and green, you can see that we have this 2D vector that looks kind of like a colored edge detection. So right now, this is currently creating vectors that are pointing away from the edges instead of flowing along the direction of the edges. So to fix that, we want to use a color matrix node to rotate the vectors. But to better explain that part, I want to quickly show how this color matrix node can be used for any transform matrix adjustments in general. So if we apply this to our original world position from our CG render, we can use any of the 3D nodes that have a world matrix dropdown. I'll use an axis node in this case. We can expression link these 9 top left parameters onto our 9 color matrix parameters. I'll pause to do that. And then if we view the position to points output to visualize the change in values by selecting the RGB, we can see that as we rotate our axis node, it's actually rotating our world position around its origin. This can be really handy in a lot of cases where we need to do transform matrix operations on our position or normals data. So in our case, we can use this same concept by rotating our 2D edge vectors along the z-axis by 90 degrees. And this will reorient our vectors to flow tangent to our edges instead of perpendicular. So finally, with all that set up, we'll lastly need to normalize our vectors so that all the lengths will be a value of 1. This is because the math I'm using inside the BlinkScript for rotating the textures is expecting all the direction vectors to have the same length. So to do that, we can use an expression node where we first calculate the length at each pixel by taking the square root of the red multiplied by itself plus the green multiplied by itself. Next, we divide the red and green by that length. And so now we have a 2D vector that can be used to reorient our brushstrokes to match with our underlying image contours. So now we can take this rotation vector setup and connect that to our original setup. I'll replace the constant placeholder with our new vectors. And then if we look at our BlinkScript result, we should now see that the rotations are coming through. However, they are a bit too high frequency. And so I find it's much better to apply a blur before the matrix nodes so that we get a much smoother result, which gives us a nice impressionistic result where we can see the more obvious features of the image coming through the flow of the brushstrokes. Lastly, I can quickly show you that you can also add any per point size adjustments by using the blue channel of our particle info input. So for example, if I connect the P mat into our world position and use that to add an offset value to our blue channel, you can start to see how I can increase or decrease the size of a specific area of particles in our image. This could also be used with the 3D position noise to add more randomness to all the particles, for example. But for now, I'm not going to use this in this setup. So finally, we have some parameters to look at on this texture BlinkScript. The size parameter will be the obvious main control, but we also have this max size, which will limit the texture from getting too big as they come close to camera. The effect kind of falls apart if we let the strokes get too close together, so we definitely want to set the max size to something lower to avoid that. The rotation is an offset value from whatever is already being provided by the particle info values. The focal length and aperture should match your render camera from before. These are being used in conjunction with the distance values that's coming through the alpha channel from the particles to calculate what size the particles should be in perspective of the camera. And then finally, I added this perspective versus screen size so that you can force the farthest particles to have some minimum value so they never completely scale to 0 in the distance from camera. This is basically mixing the natural values calculated from the aperture size and some constant value. This way you can essentially flatten your particle sizes out to a more constant screen space size. I thought this might be handy for some variations on this effect. And that's it. I'll post this setup on Nukepedia under particle brushstrokes with all the required elements. My name is Matt LaVoy. I hope you enjoyed following along with this demo, and I hope that you can take this setup and pull it apart to build your own effects using the concepts that I've shared with you. Thanks.